Good afternoon, everybody. Welcome to the third HKN IEEE Tech Talk of the semester. Thank you very much for showing up. We have a very nice full house, very exciting. My name is Ethan Hoban. I'm the president of HKN, which is the Electrical and Computer Engineering Society, and this event is being hosted jointly with IEEE, the Institute of Electronics and Electrical Engineers. Today, we have an excellent speaker, Mr. Sean Mitchell. He's an engineer from Cummins Aerospace, and he's going to be discussing topics related to and introducing guidance, navigation, and control. For those unfamiliar, it is a foundational technology that is basically covers exactly what it says. Principles and techniques to guide to targeted locations, navigate towards them, and finally, control yourself to achieve the prior two objectives. So I'll leave it to Sean from here on out, and hopefully you get something good out of the presentation. Enjoy.
That's still going, okay. Yeah, so tonight, this is just a contents of what we're going to talk about. There are just some introductions of who I am. We're going to talk about the basics of control theory, guidance, navigation, and I have an interesting little simulation that ties everything together of a 2D unmanned ground vehicle there, but that could be a car, anything that's not in the sky. And then we'll have some questions at the end. So a little about me. I'm native to this area. I've been in the defense industry for about 5 years, had a few jobs. Currently I'm with Cummins Aerospace, subcontracting over at Northrop Grumman. Several of the positions I've had in the past, specifically the Kratos and Leidos positions, I did a lot with navigation, robotics, drones, and guidance type stuff. Professionally, I focus on robotics. I do a lot of AI, ML, deep learning, and software architecture type work. Did an undergrad here at UH, finished that in 2020, and next year I finished a master's, more focus on robotics, ML, and I do research associated with ML and chaos theory, nonlinear dynamics. So that's it, my LinkedIn, basically. So tonight, like Ethan was saying, what I hope to accomplish is to give you a brief introduction to basically these three fields: control theory, navigation, and guidance. They make up GNC. That's the shorthand of it. And I want to show you kind of a practical design problem and how you can approach that. This is not a deep dive of a class. All of these three subjects you can make multiple careers out of and specializing in even sub parts of them. But hopefully, if you've never heard some of these terms before, you'll walk away, and if someone says them to you, oh, I kind of know what that might mean. So start with guidance, navigation, and control. Stands for, again, guidance, navigation, and control, which is a very broad field of engineering, and you see this in anything that moves. So spacecraft, drones, autonomous vehicles, but the point is to determine your position and control that movement. So, where you are and where you want to be. Again, these systems ensure the vehicles can reach destinations safely and efficiently, and they often follow planned paths. They correct for errors and adapt to environmental conditions. They can be very simple to just go across this room, like your Roomba, or they can be completely adaptive and be a ship that's adapting for waves, a car that's adapting to someone walking into the road, looking at you, Tesla autopilot, and various systems like that. So the complexity ranges from nothing to, beyond bleeding edge. So starting with guidance, it refers to the process of determining how to move from one location to another, usually involving generating a desired path that the vehicle should follow. They use a lot of complex algorithms to compute the required maneuvers to reach a set destination, avoid the obstacles, or follow a flight path. Some of the examples you probably have seen of a guidance system is autopilot, missile guidance, rendezvous guidance. They're anything that's saying, I need to get from point A to point B. Typically, we can further break guidance down into what's called open loop and closed loop guidance, and we'll define kind of how feedback works in one of the other sections. But essentially, open loop says that you have you don't use your sensor feedback coming in. You just say, I want to go from A to B. Closed loop says, I want to go to A to B, but I want to know where I am in relative to B while I'm going there to correct. And this will make more sense when I get to the control section. So going from there, we have navigation, which is kind of the concept of determining where you are, your current position, velocity, acceleration, orientation, things like that. It answers questions like, where am I and how fast I'm moving? So if guidance tells you, I want to get from A to B, navigation is telling you your states and kind of what's happening, how the vehicle or the object, whatever you're navigating, exists in the known universe. So some of the sensors that you use for this, because this is where your sensors start coming in, because now you're not just looking at A to B like wheels, you're looking at how do you sense reality around you. So IMUs, inertial measurement units, they use accelerometers, gyroscopes to measure your movement. Literally, if you go and shake one, it will tell you how hard you're shaking it. GPS uses satellites to tell your position globally. Star trackers and celestial navigation, if you're on the ocean or you're a spacecraft and can actually see the sky, see stars specifically. If you can see the sun, that's not as useful. Also, optical sensors, radar, LiDAR, sonar, anything you can put on the front that sends out something and says, hey, you're this far away as a ranger. So the types of navigation systems you have include, dead reckoning systems that start doing things based on previous positions and your motion data. Inertial navigation's heavily using IMUs. That's a really interesting field that I've worked some in the past. But inertial navigation is interesting because you track solely based on your previous motion. So if you are tracking where you've been, you're navigating off of that, but that can drift because you aren't getting feedback that's accurate from GPS. So it's an interesting challenge to try and navigate exclusively around that. Satellite navigation, GPS, things like that, tells you where you are, but GPS has the downside of being inaccurate to whenever you use a GPS, if you look at the data sheet for one of these, it will say, oh, I'm accurate to within so many meters, so many feet. So this is where you start combining these type of things. And then terrain reference navigation, submarines, low-flying aircraft, anything close enough to like the surroundings to say, hey, I kind of know where I am relative to what's around me. So we have guidance, navigation, and then control, the third part of it. This is how we enact our desired behavior upon that. So we have our guidance scheme of we want to go from A to B. We have our sensors to navigate us now, and now we have to do something to get that behavior to exist. So control and control theory in general deals with ensuring that we follow that trajectory but determined by the guidance system. So this is where we send signals to actuators, motors, steering devices, reaction control jets, anything like that maneuver or change where our vehicle, our object is actually how it's behaving in its setting there. These loops, these control loops continuously monitor the state positions, position, velocity, attitude, acceleration, heading, whatever, and they compare that to where we want to go. So what that means is you have sensors saying, oh, I am going, this fast at this position, and I know I need to be, based on all of the guidance and navigation, that I need to be going this much slower and be at this position. So then it can start tweaking, again, your cruise control in your car. You say it goes to 60 or 70, and the car goes faster, and it's like, okay, pull it back, or oh, I need to speed back up to reach that set point. And I'll have some slides to talk about that in a couple of sections. We can divide control. And this is not comprehensive. Control theory is a deep field into attitude control, flight control, and stability control. But basically, doing orientation, speed and position, trajectory, and its stability. So, what direction am I pointing? How fast am I going? And is this stable? If I say go to 60, am I going 60, 80, 40, or am I saying 60 plus or minus, a couple of miles per hour? So this here, I really liked this graphic, but this shows you kind of how a guidance, navigation, and control system works at a very high level. Starting on the left, right here, you have your target set point coming in that says, hey, I want to go to point A, point B, whatever. So that goes straight through here, from the guidance to the control. This plant in the far right is just the dynamics of your car. So you can think of the plant as the mathematical model of your car going down the interstate. So that, and then on the farthest right there, that last little bit that's cut off there, would be your output, position, state, velocity of the vehicle. So we siphon off that, and this is your feedback loop on the bottom. We siphon that off into your navigation sensors and algorithms, which is saying, oh, if that set point was supposed to be 70, and all of this is telling me I'm going 60, I need to accelerate. And then it goes and it pulls that back into the set point and says, hey, your error is this much. Start computing, start slowing down your car, going from there. And this is something that extends to many inputs, many things like that. You just keep going in and out. So, okay. So this is a good segue because this is also how control loops work. Again, this is a simple version of a control loop, but all of this is based on the same theory of you have a set point, you have a way to enact a change upon that, you observe what happens, in your system, in your output, and you measure those results and start comparing them back to, oh, well, where do I need to be? So this is one of our deeper dives here. It's a branch of engineering and mathematics that deals with the behavior of dynamic systems. It focuses on designing systems that automatically achieve desired behaviors in the presence of disturbances or uncertainties. So what that means is if we control something like a car and we say, hey, there's a pothole and you hit that and you drop by 10 miles per hour, does your cruise control, does your autopilot keep that speed up? Does it keep it moving there, or does it just go to 60 now and just stay there? Because it's not supposed to. You said set it at 70, it needs to stay there. Control theory is how we get that to happen. The simpler analogy might be your thermostat. If you say, thermostat's at 70 degrees in your house and it dips, during the day or goes up there, that control loop should say pull it back down or push it back up. It should keep it stable at the value. So some of the elements of control theory, and again, I can't emphasize how deep control theory is as a field. If you're an engineering degree in this school, you will see some of this, and depending on your degree, may take multiple courses on this. I took several. So elements of control theory, systems, that's the base of it. You're looking at systems, in frequency, time, any domain really, but a process, an object, or collection of elements whose behavior you want to control. And they can get as deep as you want. It can be rolling a ball across the room. It could be the mathematical model of an F-22 Raptor, which, is a lot more complicated than a ball. Another element of control theory is inputs and outputs. You have inputs, what you want to control, and for this case, the throttle position of a car. You control that. You can tell your car how fast you want to go based on that input. That is your avenue of control. And what happens, your output of that system is the speed of the car, assuming your car works correctly. So the next element is feedback. Because you have that feedback, again, continuing the car analogy, is your speedometer. That tells you, oh, well, you're going this fast. This many RPMs, this much speed coming out of the vehicle. And feedback here, measured input that's used to adjust the input to achieve a more accurate output. So as you're watching your speedometer, you're adjusting your foot, you're controlling your input and output, and that's you using the feedback. The human body and the way we interact with the universe is often, analogized to be kind of a control system. The act of walking or the act of holding something and balancing something delicate there. You're getting feedback from your senses of like, oh, well, that might tip over. Oh, my car needs to be at a different speed there. And control theory is kind of just turning that into an automatic process or something we can plug into a computer, plug into a plane, plug into something. Another big element of control theory that we're not going to talk about too much tonight, but you should know it exists, is stability and stability analysis. Stability talks about how do you return to the desired states after being disturbed. If I go and kick this table, is it going to fall apart or fall over? That's a stable system. If it doesn't, if it's unstable, it's going to collapse and change its desired state. So an unstable system may continue to diverge from a desired state when you kick it or something happens, disturbance hits the system. That's a very deep field unto itself. We're not going to talk too much about that tonight, but every time you do something with control theory, you should be aware there are many techniques to analyze the stability, and you should do that so in all cases what's going to happen, sort of. And finally, you have the controller. A controller is what takes all the feedback, takes your input, takes the outputs, does the difference of all of the mathematics and says, okay, here is the command that I need to send to the system, to the plant, that gives me a change in the output that I want to see. So, this is the generic controller that you're going to see. This covers, I won't say all cases because that's wrong. I'll say maybe 90% of cases in control theory can be solved with a PID controller. That's going to offend someone in this building, I'm sure, but probably not in this room. It's a very simple controller, but it's very powerful. It is a 3-term controller where you take your error signal and you look at the proportional gain off of it, which is the difference between your desired and your actual output. So what speed do you want, difference with what speed you're actually getting. The integration term, this center one, just says, oh, of all the errors I've been accumulating, what's the sum of it? And then that derivative term just says, how quickly do those errors change? So you're looking at how many errors do I have, how quickly are they changing, and what's the error look like right now? And this gives you a way to start making a control signal and making an input that is based on all of the feedback you're getting into your system. So, and this is another way of looking at it. This is the block diagram of it, of you have set point of, again, some arbitrary speed summed with the feedback of the output, and that pipes into the PID terms there and sums back up, goes to your process, and this gives you something you can control. This is, if you set this up and run this with a temperature sensor like a thermistor, you could have a functional thermometer. Like it's that easy, but So something else that's worth having talk here is going back to this KP and KI and KD terms there. These are gain terms. So everything else is just sum of errors, sum of time steps, but these are how you control their weights and their gains. They control how much you care about this. So if you up KP, you are saying, for my control law, I care more about the difference of the desired and actual output versus, if you up the KI or KD term. Those gains control how much you care about it in those terms. So there's a very delicate tuning art that happens here that says, okay, I need to balance these ratios. I need to make sure everything exists in a way that gives me what I want. There's a lot of ways to tune these. It's kind of a black magic, but there's some good rule of thumbs. This is what I tend to do if I'm doing a PID controller, is I start with proportional first. Just no integration, no derivative. Just say, give me a P controller, start there. What does the errors actually look like? And then I go, okay, well, I'm getting close, but I'm not getting my value. That's usually what happens, is you'll be off, but you'll be kind of stable. And then you can introduce integration control, the KI term there, and this will start to sum your errors up and pull it closer to that set point. And then finally, if I find that there's overshoot, because you often, for really simple systems, won't have overshoot. You often can just get an underdamped system and get close to the point and chase it down. But if you find that you're going over your point, and a better way to describe that is if you set your card to cruise control and you say, I want 70, and you start at 50, and it goes to 75 or 80 and then comes back to 70, that's probably bad for a lot of reasons, depending on who you actually ask. But the derivative control can pull that down and balance that up to 70. Keep that 70, keep it going there without overshooting there. Because overshoot can be bad if you're like, again, you're guiding something precise. Again, the spacecraft docking example there. If you're overshooting that and those things hit at orbital velocity, well, the space station's just gone now. You don't have that no more. Another thing you can do is you can use a kind of a trial and error approach. Sometimes if you don't have a good model, your gain tuning is going to be try a bunch of values, and if you have a good simulation, you can keep running that. If you have a flight model, you can keep running that until you don't have a flight model anymore, which sounds exactly like what you think it sounds like. Do it until it blows up. In general, if there's too much overshoot, try reducing your KP. So don't look at the difference of errors or increasing the KD. Like I said, try and keep that down. If the system responds too slowly, increase the KP. Look at, maybe I'm not comparing the errors enough, or maybe I'm not summing my errors up. If oscillations occur, reduce how much you're looking at the error or increase the KD. Basically there are rules of thumb here. This is not exhaustive, and if you have a really solid model, there are other techniques you can use that we're not going to use here because I'm trying to give you an approach to this that does not rely on model and is very empirically based. Oh, I just have raw data and untested model because that's what my experience is. We don't know the model for this. Okay, well here's a controller. Throw that in. Okay, so from there, and this will all tie back at the end, or I like to think it does. We'll go next to waypoint navigation. So we know how to control something now. We know how to have a set point and say, I want to go from point A to point B. So let's mathematically define what point A, B, C, and D is here. So for that, we're going to do what's called waypoint navigation. And it's pretty self-explanatory. We're going to define a bunch of waypoints, literally points A, B, C, D, and E, and try and make a path that goes through that. And you can probably start seeing now that, okay, so if we're using control theory to give a set point, these are maybe becoming our set points. So again, a lot of elements of waypoint navigation, and this is a subfield of navigation onto itself. You can get very deep into navigation. This is not the only way to do this, and it's probably not even the right way to do this, but it's a way that works. So there are waypoints, path planning, heading or orientation. We just did the control systems, and there's waypoint tolerances and waypoint sequencing. So we'll go through all these a little bit. Waypoints were defined as specific geographic coordinates, usually defined by latitude, longitude, and altitude in 3D space, or positions in a 2D plane where a system must pass. So kind of what does that mean? Well, any point that we can define some real measure to. You can do this without having real coordinates, and that's what we'll do in this simulation that, you know, worked when I came here today. We're gonna, you know, but in general, you know, you want a lat long or altitude or something. I'll kind of show a way to convert from lat long to something more reasonable as a concept. But this can be these waypoints can be set ahead of time if you're doing a flight plan. If anyone here flies small aircraft and has done a flight plan before, you have to tell them, oh, go from point A to point B. So you have to give the path to the airport. Say, I'm going to go down this road. They can also be assigned by operator or software in real time. I saw that at Leidos a lot, where it would generate different waypoints for some of its more complex guidance algorithms. So, which actually flows well into the next topic, path planning. Path planning is the process of defining a route through these waypoints. So now that you've said, you know, going back to this, if these waypoints have now been defined and we've said I want, you know, 1, 2, 3, 4, 5, the next step is building a path that goes through all those points. And more importantly, a path that's realistic, because looking at that, you can draw straight lines. You know, the shortest distance between 2 points is a straight line. You can do a bunch of lines there that, you know, have sharp right angle turns that just don't make much sense. And, you know, you don't want that. You want something smoother, obviously, because then a car could actually do that without having like a 0-point turn or something. So path planning refers to the process of defining a route through a series of waypoints that the system will follow. Involves considering various factors: obstacle avoidance, efficiency, which means the shortest versus the safest path. The shortest path outside this room right now at the parking lot is to jump out that window, but it's not safe. So, you know, it's kind of a, you know, to and from there. And speed too, because again, that's a metric of performance of, you know, if I can get to that parking lot, you know, out the window, out that front door, or go all the way around the back. And one of those is slower than the others. And if I'm doing my optimal criterion, I don't care as much about that. You see also, these are some of the algorithms that are used in path planning: A-star, Dijkstra's, rapidly exploring random trees and potential fields. We're just not going to go into those because we could spend 2 or 3 hours going on all of them. But I do encourage you to look into them, especially A-star and Dijkstra's, because those are very useful and very common. Potential fields are very powerful, but yeah, they're not easy. I did some of those in the spring, and they are not fun. And finally, heading and orientation. The system must be able to adjust its heading to aim for the next waypoint. If you're pointing this way and your waypoint is that way, you need to turn yourself around to get to that. For 3D systems, drones or underwater vehicles or, you know, spacecraft, space is three-dimensional, orientation also involves managing pitch, yaw, roll to maintain a stable trajectory to the next waypoint. Because you can't just be, oh, my angle's this way, well, your angle's now this path that has to wave and go through space. So some more interesting things is when you look at, going back to this again there, how do you, if you go to these points, looking at specifically, I don't know if you can see it on there, yeah, waypoint 5 over there. If you notice, we don't actually go through that blue dot in the middle of waypoint 5. So waypoint tolerance says, how close do I have to get to call that a waypoint that I met? Because if you look at waypoint 1 and 2 specifically, you kind of go square through that middle, but waypoint 5 doesn't. That's in the red circle around it. And you have to define the waypoint tolerance. What's an acceptable distance and a margin of error to actually get close to that waypoint? You don't need to pass through it depending on your application. Sometimes you want that precision, but sometimes you don't. A radius is usually a good point, but you can have different shapes depending on what you need to deal with. I worked on a project earlier this year and last year where we had to do have a robotic sled that needed to go from road to sidewalk. And the waypoint tolerances there are interesting because you couldn't necessarily do a circle because of the curve, so you actually had to have your waypoint radius almost become rectangles and be different shapes there. There was geometries to it there, but that would help us decide, as we're going into that, did we reach that waypoint that mattered? No, I said tighter tolerances may be required for precision tasks, and looser tolerances will allow for faster navigation with fewer corrections there. And if you're trying to dock with the International Space Station, it needs really tight tolerances because you're moving really fast, and physics and energy transfer still happens up there. Waypoint sequencing is very simple. It's just as you reach one waypoint, it goes on to the next one there, within the defined tolerance there, but once it's reached, it needs to shift its focus now to the next one, and the process continues iteratively until you reach the final waypoint destination. So some other interesting stuff here, obstacle avoidance, because, while this is a pretty straight path there, anyone who's watched a Roomba will know it runs into a lot of things. And anyone who's watched the internet knows that Teslas also run into a lot of things. So, sorry, not sorry for anyone who has a Tesla in this room. But basically this says that, it aims to follow a direct path, but there are obstacles that occur. In these systems that we integrate to fix this, cameras, LiDAR, radar, sonar, GPS, anything like that, help tell us, oh, there is obstacle detection and avoidance we need to do, which in some cases may be the computer going, okay, my waypoint needs to take a right angle and loop around. I need to stop. I need to just do a whole new path around that hazard, like if it's a telephone pole or something. This idea of integrating cameras and LiDAR and radar and all of this there is something that is referred to as sensor fusion. Again, not something we're going to go super deep into, but a term that you will see in this town a lot. Sensor fusion is the concept of taking all of these inputs from various sensors and making a judgment based on those. So, if your radar says you're this far away and your camera says, oh, I've detected a bounding box of that's something there, and the GPS says, oh, there's a building there, you start to fuse those and make judgments, and this can be done dynamically with weights and complex Kalman filters, things like that say, okay, based on all of my input coming in, this is where I'm at. This is how I avoid an obstacle. Again, the biological analogy is your brain is essentially a big sensor fusion suite because it is taking in information from, taste and sight and touch and hearing and smell and saying, okay, I know my general states based on that. And that's what this kind of does. It takes in all that and says, okay, the obstacle for me is not to, trip over this table when I leave the room tonight. But it's necessary for anything meaningful, to be honest, but the assumptions as we go forward tonight is that any route we look at is clear of obstacles. You will probably never find that is the case. So, I think, there's a couple more. So, this concept of waypoint look ahead, and this is a good example. Yeah, so this concept of waypoint look ahead is if you consider approaching one of these waypoints, if you go in a straight line, you have to make that really sharp right angle turn. And you can do that. You can do what's called a pivot turn, a 0-point turn, where you stop and it kind of does the crab turn and goes at the perfect right angle. But some vehicles are not set out to work that way. Most cars, for example. So the way you can get around that is by doing what's called a waypoint look ahead, which basically says as I approach this waypoint, this little inflection point right there, that I'm going to stop looking at that point and look ahead to a waypoint down the road. And that will mean that as I approach this, my waypoint, instead of going here, starts to shift its trajectory to get to that next one there. And this is another avenue of how you can control stuff here, which is really interesting because you can, if you do it this way, be ahead of your point and be a very smooth curve. But if you want to go faster, you can overshoot it and still get to that. So much like with controls where you can overshoot, undershoot, you can do that same thing here. And basically control, again, it depends on your application. If you want to get there faster, you can overshoot it and zoom into it. If you don't want to do that, you can go much slower and go from there. And then finally, So finally, we have a couple of navigation algorithms. This is kind of some classes of things that you can categorize navigation under. They have line of sight, which basically says your system, your car or whatever, is going to go in a straight line while correcting for any drifts. So, if I say walk across that room, the vehicle, the person, whatever's doing it, the Roomba, is going to correct for any natural drift that happens. This could be because the wheels are off balance, the floor is slanted, there's some mechanical error, there's some software error, something like that. So, it is an effective way if you're going to have that situation, again, the minimal obstacle situation. So we have what's called a pure pursuit algorithm. This is this is the algorithm that I implemented for the code I'll show you, and I guess after this slide. It predicts the required heading and it predicts the required heading adjustments that minimizes the difference between the distance between the current position and the waypoint. So what that basically says is I'm going to move forward and be adjusting my heading to try and get to that, to minimize where I'm at to the waypoint. So it's, you're constantly trying to zero down that, the distance between where you're at, where you want to be, and what your actual angle of, heading angle, whatever you want to call your attitude is. So, and as vector field navigation, for UAVs, this uses vector fields I don't know if anyone here is familiar with just vectors and vector fields, calculus, that type of stuff there, but it is a way to represent a function as it flows through a three-dimensional space. And the vectors have a magnitude, direction, that type of stuff there. But it uses these fields to guide the system smoothly between waypoints, minimizing sharp turns and instabilities. I've seen this used going back to the potential field navigation that's very similar to this, where you can use something similar to the mathematics and fluid dynamics and generate a organic flow of it around an obstacle. So you can say, oh, well, I have a box here, and you can say, okay, it's my model of my robot, and it will generate a flow that goes around that, much the same way of, air flowing around an obstacle, how it kind of does that, around and reconvergence there, and you can start doing things like safety margins and safety factors where, oh, I want to be this far away from my obstacle. I want to have a flow that is this much, this safe and this separated from anything that I might actually have to avoid. So we have some examples here, and before we go into that, I want to talk about one last thing here. So we talked about waypoint navigation. How would we realistically get waypoints that are meaningful to us? So, well, the starting point is the global positioning system, GPS. Probably don't need to spend too much time on this, but we have a bunch of satellites in orbit and a bunch of receivers. They sit at various inclinations and orbits, and they give us latitude and longitude, which is an angle, which is something people forget. I know I forget it sometimes. It does not give you a XY coordinate. It gives you an angle relative to some Greenwich angle, something like that. But there's a standard for it, but you're not getting you're getting a relative angle of your position relative like the equator, something like that. So anyway, the way we're going to get around this is we're going to use this universal transverse Mercator UTM, whatever. But it's a different map projection system that represents the Earth's surface in a consistent two-dimensional format. So it turns the Earth from a sphere into something more like a map, like the classical square map that you're used to seeing. It's used in cartography, geodesy, GPS applications for accurate, detailed locations and navigational purposes, and it divides the Earth into basically a grid of zones, and we do a projection over that. It has 60 longitudinal zones, 6 degrees of latitude, each covering 6 degrees of latitude, and I'll show you a picture of that in a second there. But basically, each zone is a grid unto itself that represents specific locations on Earth. So you basically have taken those angles and said, okay, unwrap the Earth, cut it into grids. Each grid now is a grid onto itself, and that is an XY coordinate. So now you have a Cartesian coordinate plane you can work with. Like I said, it uses Cartesian coordinate systems there. So this is actually really nice now, because if you try and do things with navigation in lat long, you're working with angles. And sometimes the positions of, I want to go across the room, 10 feet, you can't convert, you can, but it's easier to not have to convert, angles to feet. So if we can convert it this way into what we use easting and northing measurements there, we actually get something with a coordinate system that doesn't use negative numbers. It's all positive. It's all in rectangular stuff. It's an XY thing. And this is what that looks like. So, that's New York City that's 18 T square, but it literally cuts up the planet into squares that you could put onto a two-dimensional graph. So that gives us, okay, where's the HDMI? Is it this side? Yeah, it is. Oh, it doesn't go longer. Here, take your stuff.
Right, you're up.
Mouse. So, what I did, each conceptual. So this is something that I put together in some amount of time that we won't talk about there, because that makes me look either good or bad. But this is a Python script that, and I'm going to talk about this a little bit, and then we're going to run it. But it is going to take a object, or basically generate a path of something moving through space from these waypoints, and we're going to show what that looks like. And as we do that, we're going to use nothing but PID, basic controllers. We're not going to have anything really fancy happening there, but we're going to be able to show, like, okay, we have waypoints 1 to 7. We're going to tell it, follow this waypoint, follow its heading. That's the only things we're adjusting is its position and its heading. We're not going to touch speed or acceleration, because if you're touching position, you're kind of touching that anyway. And we'll plot that and show some interesting errors and play with the gains here and kind of show what happens as you add noise, as you add gains, things like that. So starting out here, we have just some waypoints we've established, just generic numbers. These are simple Cartesian coordinates, but now that we know what UTM exists, we could put those as actual UTM and start moving around the planet. It's just UTM gets very big and I didn't want to deal with that. We have our PID gains. This is something we have a lot of control to adjust, your proportional or derivative integration gains. Here we just have the noise level. This is just going to be Gaussian white noise. If we want to add that to show, hey, if we have a simple P controller that doesn't have any error handling, what happens if we add disturbances into it? Does it break? And we'll find out that it usually does. The waypoint tolerance is something we talked about there, of how close do we have to get. And when we run this, you'll see that, oh yeah, it actually matters. It changes how things work. So algorithmically, we're just walking through the waypoints with this, just going, okay, yeah, we have these waypoints, keep iterating through them. We're saving a bunch of our previous error states. We're computing a new error state. That's what's happening right here. Where do we want to be minus where we are. Computing some output and some gains from our PID controllers. Here we are sitting there and going, okay, well, now I need to adjust actually it's these lines here. Yeah. These two lines are saying my current X and current Y is a function of my position PID controller plus the heading. So I'm moving this much from the controller and I know I'm tilted my heading slightly that way. Then we're saving a bunch of it and then we're plotting it. So what we do, run everything. Yeah, we start and run all, that's fine. Okay. Yeah. So we run all that, and with just the simple gains that I put in there, you can see the blue here is waypoints, and you can see that red path is the route that the PID controller tried to generate. And you can already see, well, it's kind of in the shape of it there, but because we haven't tuned it well, there's all these, oscillations right here. There's these bounces, those things we don't really want. And we can see here as we look at the errors of the X and Y, we start off kind of okay, which when you look up here, it's like, oh yeah, we start off okay, but then we drift a lot. But you can see that this one here, the green, is our angle of heading, and you can see that it kind of works out okay. Same with there. So now we have this, putting this back up so you can remember it there. So we can go back to our gains up top. We can start to tweak those a little bit. So we have a full PID here, and we're taking our proportional gain up. What's my restart and run everything? Sure, that's fine. There's some key down line, they will let me do that faster. So by just taking that KP gain, we already took out a lot of our error. Like, we're already quite a bit smoother, we're dealing with all that, but we're still not quite getting where we want to go, which is the rule of thumb says, oh, well, now we need to update our proportional gain, integration gain. And this is where some of the fun of being a controls engineer comes in, is you just get to fight gains all the time. Yeah, so see, now we just keep, we start looping and we start getting straighter and straighter, and you can continue on like that and go, okay, so you can tune it. But another interesting thing we can do here is, let's just take out our I and our D terms completely. And now let's add 0.01 Gaussian white noise. And we're going to see if we do this, and we've added some noise to it, and we took out all of that. Wow, look at that. That becomes messy now. And that's just taking out that integration term, that derivative term, but, and just a proportional gain, add just the smallest amount of noise, so like a gravel road. But that really messed that up. We don't like that. So we can go back, and it's just 0.6. Start that, yeah. One day I'll learn the keybind to do that faster. So see, we start getting some differences there. Still kind of messy, but as we add our terms back in, let's up this to 4, go 2, restart. You're always going to have some mess when you start getting noise in real systems, when you include some of that stochastic stuff. But see, now we're getting back to like, oh, we're getting more stability again. We're getting a way to handle all of that noise we were seeing before. And you can sit there and play with this. And this code will be provided too, so you can sit here and play with all of the the gain terms, and you can add waypoints. We can sit there and change, like let's change this middle one to 9 and 15. And let's see what it does. Restart and run all. Maybe this breaks it, that'd be funny. Yeah, see? So it makes a path and goes all the way out here, captures it and tries to come back there. So, you know, and that's, you know, the only thing that I see happening wrong up there is it's probably a very sharp turn. But if you controlled your steering rates, it would be forced to, you know, loop back around in a reasonable way. You know, if it wasn't a robot that could, you know, do a 0-point pivot turn. But you can start to see where all you have to do once you have some of these loops set up, all we're doing is tuning a gain value, and you know we've tweaked our waypoints, things like that, and that's just to give you, you know, that's all you have to do to control it. Now I will say, you know, before you think this is the end all, which you probably don't after looking at these plots, this is a little bit bad form as far as control theory goes. If you're doing control theory properly, you know, and this is not proper, you should have a model, you should have something mathematical you can operate on, because that opens up stability analysis, it opens up optimal control, and really setting up your functions and your control laws in a way that are perfect for your specific vehicle, your specific application. This is simply saying, I have data coming in, like off a little Roomba, and I don't know anything about it. I don't know anything about the model. I don't know what it looks like mathematically. I can make some assumptions, but this is a way to say, okay, throw in the measurement of where I'm at in my current heading and start to control it off of that. So this is never going to give you the optimal solution, which you can see, you know, kind of with that there. The other thing we can do that I just remembered, we can play with the tolerances. So if I take remember, the waypoint tolerance is how close we have to get to a waypoint to say we captured it, we hit that point. So if you notice there, when I make the waypoint tolerance really big, it has very smooth curves, like it goes that place, but we miss it by, you know, 0.5 or whatever I just put the waypoint tolerance at there. So it's like, oh, well, it's much smoother, it's much, you know, much less precise, but you're still getting to the point. It's just smooth. But if I go and make the waypoint tolerance, you know, very small, restart and run. So see, if I do that and make it very small, it's getting a lot closer, but it also is introducing noise and possible errors, which, you know, again, you might be able to tune that out. That might be a case of having to go, oh, well, if I get really close to this one point, you know, and it has to say, oh, only detect it if you're really, really close. If you're 1 micron close to it, if you never get 1 micron, but you get 2 microns, you're just going to keep looping around that point. So it's a trade-off. And that's the thing that you figure out very quickly with navigation and GNC in general, is a lot of these are functions of trade-offs. There's a trade space of how fast you want to get there. How accurate do you want to get there? You know, can you get there with this vehicle type there? You know, and this is where you can start going, oh, well, maybe this algorithm works, but I just need to change up my vehicle structure. Maybe I need to have something different, you know, in my design of my vehicle. And, you know, this is where cross-functional teams become very powerful. So, what do I have after that? Did I have anything else? Kind of some conclusions. Yeah, so acknowledgements, give those out. UAH, IEEE, Ethan for helping set this up, HKN for helping set this up. There's a sign out, and we can do questions, because questions are always fun. I like being roasted. You want me to leave the sign out up, or?
Real quick. Round of applause. As Sean mentioned, that Jupyter Notebook and all that code will be provided. There'll be a GitHub link that everyone can get, but in order to get that GitHub link, you gotta sign out. So I have the email list so everyone can get access to that code. But
there we go.
In the meantime, feel free to ask questions.
Or just insult me if I did badly. I mean, I don't care. I work 980 into my week there, so if we want to just, you know, go at it, I don't care.
I have a question.
Sure.
So I used to work in like industrial control systems, and definitely experienced what you do when it comes to tuning parameters, where with control valves or other things like that, yeah, you basically set the, kind of watch it, maybe add a little I, almost never have to, in that setting, have to use derivative control whatsoever.
Yeah.
So in your experience, and what does that look like? What are those kind of typical parameters for something like this, like vehicle navigation and other things like that? Do you find yourself having to kind of just go with that box standard stuff, or do you oftentimes have to be more detailed in figuring that out?
I think it depends on where you are in the design process, especially if you're going from prototype to a deliverable product. There's a few rules of thumb, of like, oh, maybe try your PI at 2, or your KP at 2, your KI at 0.6. There's a few, like you can run some rule of thumbs, mathematical formulas that say, 70% of the time, this formula will give you like a reasonable gain. But the art of tuning is getting it right to your system. If your system is very imprecise, like some of these simulations of like, well, that's good enough, then, kind of checking guessing works fine. But like you said, working with valves and things like that, there's a lot of precision there, because if your pressure changes, then, that's an exploded box. So, it really, I want to cop out and say it depends on the problem space, but it does. I definitely think that, in my experiences, the more complex your navigational problem is, the more you do need that derivative term. For simple stuff like the little sled thing with the road I was mentioning earlier, we ran that with a PI controller, like PI with like some low pass filtering over it. So it wasn't particularly intensive. We could kind of check and guess that. Wasn't crazy gains there. That was like a 4 point something and a 1 point something. So very simple stuff. But if that had been more complex, or had a more complex job description, to back up some context for that we were designing a sled that would work on self-driving car test courses to pull out in front of a vehicle with a test dummy and force the self-driving cars to stop. So we were making a test harness. But that's a very simple problem of like, go to waypoints, come out in front of this, and, basically not get hit yourself. But if that had been, flying, it'd been like a drone or something complex, or had a lot of really complex, error states, a lot of obstacles to avoid, that derivative term really could have come in handy. Another case it could have been handy is that if that thing moved fast, I think it could go 30 miles per hour, but we never pushed it past about 15, mostly out of fear. We tried it at 15 and it was kind of scary. Could probably take someone's shins out pretty easily. So if you start going faster, then those error terms accumulate up quickly. But yeah, in my experience, PID covers most of it. I think PI covers probably 75% of it, but your mileage would definitely vary, and don't quote me on that, because I don't want to be guilty of an exploding car or something. So,
Thank you.
yeah.
You're doing your masters in controls.
More robotics and artificial intelligence, deep learning type stuff. But my undergrad focus, I took some extra controls and robotics when they were still being offered here, with Corsetti and Picarillo and Stetzel. Some of those professors, I guess some of them are retired by now. So, but yeah, I did not get to take any controls at the graduate level. The semester timing never worked out. So there's some really good controls professors here. If you're interested in the subject, a lot of really smart people, a lot of really good research happening here with that. So.
You're talking about GPS. You mentioned a lot about the Mercator coordinate system.
UTM.
Is there really any functional difference between that and bullet coordinates?
A little bit there. UTM kind of puts it in my experience, a more convenient XY format. Polar coordinates, I think, you're still dealing with angles, you're dealing with sine and cosine type trig functions, if I remember correctly. And UTM can give you a very much just, here is a grid, X, Y, Z, of you are it, point X, point Y, which if you're trying to view, again, a 2D vehicle on the ground from above, that's what you're dealing with there. But if you're trying to go, okay, I want this 2D vehicle to go forward 100 feet. Well, what's 100 feet in angle, relative to satellites moving on the Earth? It's just kind of a weird conversion. And in my experience, again, because I'm dumb, a lot of times things just fall out of like, oh, well, I forgot an angle here. I forgot this was actually not an angle. And, I mean, we've seen that at work a couple of times where angles become annoying with lat long. So
Geodetic coordinate
yeah.
systems. That's
So, it's and that's a point there. If once you get into like complex problems, we'll say rocketry type stuff, you might be working with multiple, things from the ground to space to in the air, a lot of frames, and simplifying how many coordinate transforms you have to do is always better because those are expensive mathematically, like in a computer. They're sine and cosines, they're usually numerical algorithms, so the more you do, especially in real time, if I need to know I'm constantly here, well, you're constantly running that numerical algorithm. So if you're transferring from coordinate A to B to C to E back all the way down, that gets expensive, and the math just gets hard because by the time you're up at the 5th coordinate transform, it's like, well, what does that actually represent relative to where you were on the ground for this thing moving at high velocity? So I like UTM for 2D stuff, but that's not a lot of, that's only part of what you do with guidance and navigation. Obviously with this town, rockets, missiles, drones, oh my, that type of stuff. So.
Well, the other issue that you have going from that long to just traditional polar spherical coordinates is that the Earth is not a sphere.
Yeah, that's true. There's an approximation.
Non-linear terms, or those non-spherical terms. And there's one particular thing I think I can't remember which one it is, but actually doesn't converge very easily. So.
Yeah, the Earth has to be viewed kind of an approximation there. So when you start looking at, what's the surface area of a sphere? Well, it's like, well, that's not the Earth. We're kind of potato-y shaped, squished about like the equator and all that.
Wider than the equator.
Yeah, it's, yeah, gravity is,
Yeah.
something like that. That's a good question, though. It's the coordinate transforms are probably one of the hardest portions of GNC in my experience, is just figuring out how to mathematically describe where you are right now and how to represent that. Because like controls is not too bad. I mean, it will when you get to like nonlinear and adaptive and the weird stuff, but just the basic of you're here and you want to be here, make it go there is not that bad. But figuring out, well, what does that mean? What dimensions do you look at? What do you care about? How do you get there? Anyone who's taken calculus has probably done I convert to polar and spherical and Cartesian. It's like, that in real time, constantly iterating over is, it gets messy. So.
You said you could, I guess, guidance, navigation, control can be very broad, but within all three, you can kind of get into subsections and really specialize in something.
Mm-hmm.
In your work experience, do you find that you spend like your time in guidance, or is it pretty much every time you come to a new problem, you're just going to hit all three?
That's a really good question there. I'm not trying to like cop out on this one. In my experience, when I'm approached with a problem like this, I find myself thinking much more in the guidance and the navigational terms. Like I said, a lot of things with controls can be simplified to a simple PID controller. If you really want to extend that, you can do what's called a PID-F controller, which has a low-pass filter, which stabilizes that even further. That captures so much of your basic stuff that if you can really nail down what you're trying to, where you're at, where you're trying to go, and how you're trying to get there, having the controller go, okay, well, I have my set points, I have my data, I'm just going to pipe it there. Again, this doesn't work for really complex things. A jet fighter is moving so fast that some of these controllers like PIDs they don't keep up there, and you need more robust controllers in that situation. But I find that for me, it's really just, okay, how do I, programmatically, because I spend a lot of time in software more than hardware now, programmatically, how do I describe where I'm at and how I want to make that be something I can move elsewhere? How do I define that? How do I set that up? How do I store all that information? I don't find myself thinking in controls a lot, but like this gentleman, if I worked much more in industrial controls, I'd be thinking about that a lot more because again, if a valve explodes, then the factory explodes. So you care a little bit more about that. But in general, I think that the guidance and the navigation part, particularly I would say probably some of the guidance and the algorithmic stuff is what I think of mostly. But that's a good question.
One really interesting thing I find about GNC stuff is like the thought process of how different like space navigation is to on Earth navigation.
Mm-hmm.
Because once you go out of orbit, you lose all GPS. You can no longer use GPS.
Yeah.
So you have to rely so much more on like dead reckoning calculations. So like, do you have any kind of experience with dead reckoning projects and that sort of thing?
Yeah, I've had some. When I was at Leidos, that whole division I was in was a lot of R&D stuff. They worked heavily with GPS-denied navigation and ML-based navigation. If you're interested in this kind of stuff, definitely look at Leidos there. They have a strong group with a lot of interesting work there that goes on sometimes. But they worked across a lot of different platforms and, theaters, defense contractor, obviously. And some of the stuff that, I had to do with them there, I made star trackers with them. We had to go out at night and, drive through the country and basically verify, like, hey, could this thing that might be going on top of an aircraft that might be flying over, enemy territory, high at night, can it track the stars that it actually sees and goes from there? And you're right, as you get into space, you do lose things like GPS, and you have to rely on, like, information from the ground and ground stations. You have to rely on star trackers. And there, when you're prototyping and building stuff, you have to consider that, because not every vehicle is going to have the same sensor suite. It's not going to have the same domain that it works in there. If you're making a big, giant, unmanned submersible, then you have to remember that that's not going to have the same abilities sensor-wise that exist on a car. GPS and some of your communications may be harder to get through the ocean. Star Trek is probably not going to be that useful at the bottom of the ocean. But the terrain-based stuff of I'm navigating based on the ocean floor, and there's maps of that, some maps of that there. So yeah, you have to. That's a really big point. Part of this is if you're designing a GNC system, of understanding where you're going to be actually using it. At Leidos, I was working on planes. I did some stuff with the Office of Naval Research. Did some stuff for soldiers' backpacks. Did ground stuff. Did everything but space basically. Wish I had done some of the space stuff there, but they didn't put me on those fun projects. Hence why I don't work there anymore. So, but yeah, so it that's a really good question though. But I agree with that. Some of the sensors that exist now. I took a navigational class here at UAH over summer. And the guy talked a lot about gravitational and magnetic navigation there. So using magnetometers to make magnetic maps and localizing your robot or your vehicle based on H fields. And then, the gravitational type stuff too, of being able to generate that map locally based around that, which can be great for, a spacecraft there, because as you start moving through, space and you have all these different gravity lanes, things like that, it's like, oh, well, there's some navigation that you can do there at a macro level, because you're much more sensitive to things like gravity measurements when you aren't swamped by gravity on Earth there, because, gravity right now is, functionally 10 meters per second squared there. Offend someone with that, I'm sure. But, there's a lot of ways you can do it, so, Anything else?
Note, if you want to do magnetic navigation, the World Magnetic Model is an 8 megabyte header file for C++, and you can download it from the NOAA website. So you can have the entire Earth's magnetic model, 8 megabytes. Good luck putting that on an archive.
I will say with magnetic navigation, if you do go and measure with a magnetometer, which some of your phones probably have that, you want to do that out in the middle of a forest, because I made the mistake of doing that through a neighborhood, and it turns out houses and cars are very magnetic. So, and I was grateful the professor did not fail me over that. So, learn my lesson and remember that most things are ferrous and provide some magnetic fields. Also, don't take that hike in the middle of summer in Alabama, because it's quite warm. Anything else? Questions about me or what I do, or, anything I rambled on for too long about, I'm sure?
Another round of applause.